Assalamualaikum and very good afternoon to all my friends and our aircraft design to lecturers. So today I would like to do a presentation of our aircraft design to project. This is my group members. We have 14 of them, and so let's start with the objective of this subject. The first one is to design a real working aircraft. To generate the detailed structure and design of the main component of the aircraft, we need to also analyze the loads acting on the structural aircraft. Next one is to design an aircraft system component such as the control system, the avionics, the power control system. And for this case, we need to design an electronic system for our RC plane to work. And the next one is to prepare assembly drawing of the aircraft A-frame and to demonstrate the ability to think critically and solve the problems with regards to the aircraft design. We need to also adopt the ability to work together in a team and to produce the aircraft design. And the last one is to demonstrate the ability to present our ideas and also our solutions. So let's start with the preliminary and conceptual design. So the first one is we decide to have a rectangular wing for our aircraft RC plane. This is because of it is the most wing configuration among the aircraft. It is also the simplest wing to manufacture, and also by having a non-tapered wing, it is suitable for a light aircraft, and for this case, it is suitable for an RC plane. It is also easy to design and also easy to maintain and to carry more fuel in the wing part. The next one is the fuselage configuration. We are having a monocoque configuration, which is relies largely on the strength of the skin to carry primary loads. So for our aircraft design, our skin is using the EPP foam, which is its durability is very high, and also it is quite strong to support the fuselage. The second one is using the former bulkhead and also the frame to give shape to the fuselage. As you can see, this is the bulkhead to hold the motor. This is the former to hold the fuselage, and also the skin to cover the former. The next one is it is also the heaviest located at the intervals to carry the concentrated loads. So for this case, the heaviest located at the intervals to carry the wing at the middle part. And also the final one is the design is simple and also easy to fabricate. And the next one is the tail configuration. We are having a conventional configuration because of it is also most common form. It is also provides the adequate stability and control with the lowest structural weight. It having a low risk and ease to control, easy for manufacturability, and the last one is most efficient for speed RC plane. And the last one is the landing gear configuration. We are having a tricycle configuration, and also it is most common form as well. It prevents the nosing over when the aircraft brakes and enable a higher landing speed. So by having this configuration, we can prevent the problem of nosing over when the aircraft land on the ground. It can also provide better visibility during landing and maneuvering. So this case is for real aircraft. Prevent the ground looping and also most efficient for speed RC plane. So this the roughly schematic diagram of our electronics, the battery, the ESC, motor, transmitter, receiver, and also the servo. And this is the material selection. We are using EPP foam and also the plywood for the former and also for the rib of the wing. And this is the weight and cost estimation before we start the project. So for the weight estimation, we are having 1.467 kilogram, and also for the cost estimation, we need around 382 ringgit and 86 cents. And this is the aircraft specification for the rough design. We are having a wingspan of 1.2 meter. The mid aerodynamic chord is around 0.17 meter, and also the fuselage length we have 0.73 meter. We are using NACA 2412, having an aspect ratio of 7.06 the wing area of 0.204, and also the dehydrate angle we are using 0 degree angle. And this is the overall aircraft drawing. We're having the wingspan, the rectangular shape of the wing, the conventional tail, and also the size of the propeller. So that's all from me. Thank you.
Very good evening. Greetings everyone. So my name is Shama Devi, and today we're going to present about the electronics and also the center of gravity. So for the electronics, we have a few electronics components. The first one is the LiPo battery. So we are using a Max Power brand, which has a 4-cell. It's a 4-cell battery which consists of 14.8 volt, and it's a 2,200 milliampere per second with 35 C. And the next one is we are using this ESC, it's a Skywalker 30 ampere ESC, and the propeller is APC 9045 propeller. So this propeller and also this ESC is chosen based on the given model specification, which we are choosing Sky X2216 1100 kilowatt, and we are using the servo, 4 servos for 4 control surfaces. This is a plastic servo. Why we are using plastic servo over metal servo? Because plastic servo is cheaper. It's cheaper compared to the metal servo. And then we are using this FSI A660H 2.4 GHz receiver. We are using this with a Fly Sky transmitter because both are compatible. And the next is the center of gravity. So a few calculations has been done for the propeller, motor, wing, horizontal tail, vertical tail, fuselage, front landing gear, back landing gear, ESC, LiPo battery, servos, and also receivers. So calculation has been done to get the center of gravity for each of these items. So this is where all this center of gravity is located. For the CG for the propeller is in front, then ESC, then the CG of the engine, then the horizontal tail, and then the CG for the landing gear, and also for the servos and fuselage. Thank you. That's all.
Assalamualaikum. My name is Muhammad Nasrul, and today I will proceed our presentation with propulsion and performance. For propulsion and performance, our subgroup is Amirul Amin, Muhammad Nasrul, Azmi, and Nurul Afifah. First, we'll go to the motor selection. An important criteria in selecting motor is a thrust to weight ratio, which is depend on the type of the aircraft. As you can see, this is the table type of aircraft and thrust to weight ratio. We have a glider, scale flight, sport and slow acrobatic, fast, and jet and trailing. And then based on the table, see that our aircraft and our project is for scale flight. So the suitable thrust to weight ratio, that's our aircraft is 0.6 to 0.7. To calculate the necessary thrust of the aircraft, the following formula is used: thrust equals to weight time thrust over weight. See, the maximum weight of our aircraft in our project will not be more than 500 grams or less than 500 kg. And then the necessary thrust is we choose 1.5 kg as our weight times 0.6 thrust to weight ratio, and therefore we have 900 G of thrust for takeoff. And then we have kV and characteristic of aircraft table. We have 1000 kV of motor, 2000, 3000, and 4000. Since our aircraft need to have a higher thrust and a higher speed, so the motor with the kV value of 1000 or 1000 to 1400 is chosen. And then an experiment regarding the power thrust ratio has been done by Victor 2017 to determine the suitable power thrust ratio with given value of kV. So the kV of motor we choose 1000, and then our power thrust ratio will be around 0.26. Okay, so based on the graph, we obtain the power thrust ratio is 0.26. And then our power required for our aircraft will be around 234 watt. So from this calculated value, there are two selection that we can choose for our motor, which is the Teknologi and Sunny Sky, which have the maximum power of 336 watt and 385 watt. But the Teknologi is not available in Malaysia, therefore we choose Sunny Sky as 2216. So the weight of the motor will be 72 gram, and then maximum thrust available 1380 G. And then the power selection. So for propeller selection, this given by the manufacturer catalog. So will be for propeller will be APC 9045.
So for our power required and power available, we use this equation to calculate it. So for this one, this is the theoretical thrust that we calculate. So the total list will be 1316 gram force, and this is the coefficient of C, air density dependent coefficient at 20 degrees Celsius at 1 atmospheric. It is 0.0278, and we use the efficiency of the motor and the propeller. It would be around 70%. So the actual power available that will be supplied by the motor is 100.8 watt. So next is on the power required and the power available graph. So as we can see, this is a power available and this is the power required. For the rate of climb, we have the maximum. The rate of climb max is 2.9 at 7, and from the graph power versus V, we got the maximum excess power at 58.56 watt at 14 millimeter per second. Sorry. So this is the graph for rate of climb against velocity. So next is on endurance and range. So we calculate the endurance based on the battery capacity. So have 4S, since we use 4-cell battery, so we divided by 1000 times by 0.8, so 80% of it will be used. And then 35A is our discharge rate, so the total will be around 12 minutes. And the range we calculated by endurance times by the velocity, we got around 10,000 meters. So for the takeoff we got around 10.58 meter, which is good. And for the landing, we got around approximately 17 meter. This value could be more or less, as we haven't tried the flight test yet.
Okay, Assalamualaikum to my friend. So my name is Muhammad Hanif Shah, as a representative for subgroup of tail and fuselage design. So my group member is Ahmad Fakrul Razi and Muhammad Hafiz Ahmad. So first, we will talk about weight and loading on an aircraft. So here, as previous slide, as said by Samala, there is a type of things as we apply in our RC. So the weight is being set at the location where the CG of the thing. So the total of takeoff weight is, as mentioned earlier, 1,500 plus minus with 100 gram, as well as empty weight of the RC is 1,000 gram. So in the shear force and bending moment diagram, so as we can see, this is the condition we take as a cruising condition while the aircraft is in the air. So the gravity is for 1. So as well as the speed at 14 meter per second. where the maximum shear force for this condition is 6.4 Newton, whereas the bending moment is negative 0.48. So for next is 3G with the same condition as previous. There is change in the shear force with 19 Newton, and the bending moment is about negative 1.4. It being increased is different from the earlier gravity because of the different force acting on the lift. So for condition of negative 1.5, we have 5.37 as the positive maximum for the shear force, but the negative one is negative 9.61. For the bending moment is positive 0.7. All this calculation actually is available, applicable for our design, which has which can counter the shear force and bending moment. Same goes to the tail. For now, as you can see, the lift is 1.14 Newton per meter. This is a diagram of the front view of the RC for the tail. So the condition also 1G. The length of our tail is there. So by drawing the VN diagram, we can get that the maximum and minimum is almost the same, whereas the bending moment is negative 0.05, is small, quite small. So for the 3G, there is increase in the lift, but the force in the bending shear force is 0.5, approximate to 0.6, and for the bending is negative 0.036. It's quite small, so it will not damage the tail. And next, we proceed to our G when the G is negative 1.5, which is the aircraft is flying upside down. So the maximum value is negative 0.9, which is approximate to 1 only, 1 Newton. Okay, so for the bending is negative 0.17, which is also considered as 0, approximately to 0, which is not given disrupt for the RC. Okay, so we proceed to our membership, which is G.
Okay, Assalamualaikum and very good afternoon. My name is Ahmad Abrazi. So today I would like to proceed my presentation with fuselage tail manufacturing process and component fitting and material selection. So first, for manufacturing process, we start with our process, which is we draw the template on the EPP foam, and then we proceed to the cutting process where we use the knife to cut the template that we already draw on the EPP foam, and then we cut all the parts, and then we proceed to sanding process. And then for the tail installation, we attach the vertical stabilizer with the rudder using the fiber tape, and horizontal stabilizer with the elevator with the fiber tape. And then for fuselage installation, we use the hot glue gun to attach the former here with the fuselage. We use the hot glue gun to attach between them. And then this is the final assemble of fuselage tail. As you can see here, this is fuselage and this is our tail, and this is the fuselage only, and then this is horizontal tail and vertical tail. And then, so for fuselage structure, we use monocoque structure as our first presenter already mentioned why we use the monocoque structure. So it's because it largely on the strength of the skin to carry the primary load, and the design is simple and easy to fabricate. So for monocoque structure, it's a construction of uses of former frame assemblies and bulkhead. As you can see here, we have two formers, which is we use the plywood 3 mm of the thickness, and one bulkhead with use of plywood also 3 mm, and our skin is from EPP foam, which is 5 mm thickness. And as you can see here, this is the battery tray where we're going to put our battery. We use EPP foam also, and this thing, the black color here, is the battery holder where the battery will be held using the Velcro tape. And also this part is the servo platform. This is our internal structure of our fuselage. Then for tail, we use the conventional tail, and also already mentioned by our first presenter, is because it's the most common form and most efficient for the speed RC plane are expected to fly. So for horizontal stabilizer, we use the EPP foam, and also the elevator also use EPP foam, and we attach this. As you can see here, this is the fiber tape we use to attach between them, and also this the vertical stabilizer and also the rudder, we attach them using the fiber tape also. So for the material properties, the wing part will explain because we use the same material, same as them. So thank you.
Good afternoon to Dr. Nasri and Dr. Wan Zaidi and my fellow friends. Today I'm going to present wing design of our aircraft. So this is our aircraft, as you can see over here. The type of our aircraft is a high wing aircraft. And then the reason that we choose high wing is because high wing as compared to low wing aircraft, high wing aircraft will have a better inherent lateral stability. So when there is a turbulence, the high wing aircraft will try to right itself. And then this is because the center of gravity for the high wing aircraft is below the wing. So this is better as compared to the low wing aircraft. And for the low wing aircraft, it incurs more ground effects to the aircraft, and it makes the landing less precise. And then for the airport selection, we are using NACA 2412, which is a cambered airport. That means we will have a higher amount of lift as compared to symmetrical airport. Next, these are all the dimensions of the aircraft wing. And then for our twist angle, as our aircraft is very small, so the wing, consider that the twist angle is close to 0. So this is the diagram of our NACA, which is NACA 2412. This is our wing components. Our wing is made up of this rib, spar, skin, and aileron. So this is the diagram of our rib, made up of two cells, A1 and A2. And then the spar is located 0.3 C after the leading edge. And this is the plan view of our wing. As you can see over here, there are four ribs here, 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 and here. Okay, and then the spar is at the middle of the wing, and we have two ailerons at both wing tips. So this is the exploded view of our wing. This is our rib sizing. Okay. And then this will be our spar sizing. As you can see over here, the cross section of our spar is rectangular because our aircraft wing is quite small, so it is not appropriate to use I-beam or C-beam. Next, these are the material selection of our wing components. The rib is made up of plywood, and then the skin, spar, and aileron are made up of expanded polypropylene EPP foam. So the following is the material properties for EPP foam and plywood. Okay, for the project requirement, our project requirement is set where the maximum takeoff weight is less than 5 kg, while the positive load factor is positive 3, negative load factor is negative 1.5, and this is in the range of according to the Civil Aviation Regulation (FAR). Since the positive load factor is positive 4.4 and negative load factor is negative 1.76, so it is in the range. And our maximum takeoff weight is less than 5 kg, and in our project we will try to achieve 1.5 kg. And our aircraft has the purpose of utility, so we refer to section 14 of the FAR. So let's go into the loading calculation, but before that, we need to determine the DN diagram, which is our flight envelope. Okay, there are 4 critical positions of the aircraft during flight, which is here, 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 and here. So this is A, D, E, and G. So they have in this position, the aircraft will have 4 different critical speed. So beyond the speed, the aircraft structure will deteriorate and fail. So the BA is 16.5, BD is 33.6, DE is 33.6 also, DG is 16.3. So the VN diagram you can see over here has a positive load factor of positive 3 and the negative load factor of negative 1.5, which is according to our project requirement. It meets the project requirement. And then from here, we can get the velocity, the speed of the aircraft. With the loading factor, we can determine the value of our lift coefficient, CL value. And then so based on our NACA 2412, we can just refer to the graph of CL versus alpha graph to get the value of alpha, which is our angle of attack. So with the value of angle of attack, we can get the value of Cn. Cn is the normal lift coefficient, okay, by using this equation. Okay, this equation is based on here, this diagram. As you can see over here, once you have resolved the force, lift, okay, and CL and the D, which is the CL and the CD, you can get the resultant aerodynamic force, which is the N, normal lift. So once we got the Cn, the value of Cn, we can simply obtain the value of normal lift by using this equation. Okay, once after we have obtained the value of normal lift, we can simply calculate for the shear load and the bending moment. So this is the graph of how to obtain the lift coefficient value and the CD coefficient just based on the value of alpha. Okay, so for this calculation is based on the wing section without aileron. But what if there's aileron? So with aileron, there will be a delta CL. That means there will be a change in the lift coefficient value. As you can see over here, there are 2 ailerons over here. It's the part of the wing where there is aileron. So the aileron function is used to control the roll. Okay, so when the aileron deflects downward, there will be an increase in the lift. But once it deflects upward, there will be a decrease in the lift. So the delta CL, either that is to increase or decrease, is based on this equation. This is taken by McCormick equation. After that, we can just repeat the procedure like the wing section without aileron to get the normal lift, shear load, and the bending moment. Next, about the torsion. For the torsion, we have using the alpha angle of attack, we can get the lift coefficient. Okay, with the lift coefficient, we can simply get the Cm value. Here we can get the Cm value. That is for the wing section without aileron. with the value of Cm, we can substitute into this equation, torsion equation, to get the value of torsion. But when there is aileron, for the wing section with aileron, there is a delta Cm. That means there will be a change in the value of moment coefficient. How to determine the delta Cm is based on this graph. As you can see over here, when there is a deflection of the aileron downwards, the graph will shift down. And how much is shift down? Depends on the angle of deflection of the aileron. So we can get the delta Cm. So it will change the result of the torsion. So after we have calculated the normal lift, the bending moment, shear force, and torsion, we can simply plot the diagram. So I would like to explain a little bit about the diagram. So for the normal lift across the wingspan, for the wing section without aileron, the normal lift is constant, as you can see over here. Okay, this is because the alpha, the angle of attack, is constant across the part without aileron. But once there is an aileron, there will be an increase in the normal lift. This is because of the increase in the CL value. And for the maximum is when the aileron deflects down and it's at position D, because the critical speed is the highest. Okay, it's the highest, and the log factor is the highest, which is +3. And from there we can get the moment and the shear force across the wingspan, as you can see over here. And then for the torsion, same as the normal lift across the wingspan. For the wing section without aileron, it's constant. But once there is an aileron, there will be an increase in the torsion and also a decrease in the torsion. Depends on the aileron deflection. Okay, next I'll go into the stress calculation about the spar. For the loading on spar, okay, the loadings on the spar are shear and bending. Okay, shear and bending. So the spar is over here, 60 cm. Okay, from here we can get from the previous calculation, we can get the maximum shear and bending moment. We just simply substitute into the equation, sigma equals to my over I and tau equals to b over a, to get the loading. And we also calculate for the critical buckling strength, FCR, and then we compare the critical buckling strength and the loading to get the factor of safety, to determine if the structure is safe or not. And then I will also talk about the stress calculation for the rib. For the rib, as I have mentioned before, is divided into 2 cells. The space in front of the spar is cell 1, while the space behind the spar is cell 2. So we just split into 2. For this lift distribution, we obtain the lift distribution from the pressure distribution acting on the wing. So as we all know that the lower part has a higher pressure than the upper part. So actually the graph is more complicated than this, but for our aircraft, it is very small. Our wing is very small, so we can simply simplify our problem and get the lift distribution like this. Once we split, we'll have a log distribution like that, clockwise log distribution like that. Okay. After that, we can simply, based on the diagram, we can get the equation of the bending moment and the shear. Okay. From there, we can just substitute into the equation of the loading, sigma equals to my over I for bending, tau equals to b over a for shear, and then we get the strength, the critical buckling strength, to obtain the factor of safety. So this will be next I will talk about the stress calculation of the skin. Okay, for the upper skin, the loading on the upper skin are combined shear and compression. For lower skin, it is combined shear and tension. As you can see over here, this is compression, and from here, the lower part is tension. But for the whole skin, there is a shear. So we need to calculate based on just like the previous calculation, to get the loading and the value of the critical buckling strength, and we can simply get the factor of safety. So So this will be the shear, how to get shear due to the single cell section. We can simply get the tau, which is equals to the Q over T, which is the shear flow over the thickness. And then not just the shear flow due to shear, we also need to calculate for the shear flow due to torsion. And after that, we just simply plus together the shear and the torsion to get the safety of vector. So after we get the safety of vector safety, we can see that all of the values are more than 1. So that means since the factor of safety is more than 1, the wing structure is safe. Okay, next I'll pass to my group member to continue.
Very good evening to the lecturer and all students. My name is Muhammad Shafiz. I represent to the wing attachment component. Here is component attachment and fitting for the wing to the fuselage. Here you can see this isometric view of the wing, which is attached to the fuselage by using screw. Here is a gypsum screw. Hot glue gun are using to attach the wing and the spar inside the wing, and we use fiber tape to attach the aileron. Here is the manufacturing process. The apparatus for the manufacturing of the wing, we are using hot iron, fiber tape, heat gun, and metal part, CA glue, and also solder for the electronic part. For the main component, which is the wing skin, we are using 5mm EVP foam. We are cutting the EVP foam according to the wing size, and then we fold together. For the spar, we are using 5mm of EVP foam and 3mm plywood. The 3mm plywood are using to support the spar and both sides of the spar. Then we are having a rib which is in airfoil shape. We are using airfoil former. We are printing the airfoil in the sheet of paper, and then we cut the airfoil by using 3mm plywood material. For the wing tip, we are using 5mm EVP foam. We have 4 for the right side and 4 for the left side. Each of the EVP foam are combined together by using hot glue gun, and we sandpaper it to get a smooth surface. And then for the aileron, we are using the 3mm EVP foam from the wing skin. We are cutting it from the wing skin, and then we are using fiber tape to attach the aileron to be can be deflected. For the wing mounting, we are using 3cm gypsum screw, 5cm gypsum screw, and also black decal. The screw are functioning to attach the wing and the fuselage, and the black decal are to mark the position of the attachment. And then for the electrical component, we are having servo, wire, and also rod. For the servo, is using to deflect the aileron. The wire is to supply the electrical current from the battery to the servo, and also rod to pull the aileron from the servo. Here is the costing part of the aircraft. Okay, we consist of 4 main part of costing, which is propulsion and engine, electronics, fuselage, wing tail, and also payload. For the propulsion and engine, we are using motor Sunny Sky X2216 and also propeller blade, which is the before the project started, we are assuming the price of all the item, which is for the propulsion and engine, we are assuming 120. But after the purchase has been made, we get the price for 88 ringgit. And then for the electronic part, we are consist of 4 servo, 1 Fly Sky FSI 6 receiver, depot battery, 3 cell, 2200 milliamp per hour, ESC30 enter, and also 4 push rod with wires. Here is the cost for the assumption before the project, but after the purchase has been made, we are find out that the total for the electronic part is 161 and 80 cents. For the fuselage wing and tail, we are using 2 polyfoam and also 3 plywood. 40 ringgit and 15 ringgit for the polyfoam and also plywood respectively assumption for the price, but after purchase agreement we are paying for 97 ringgit. For the payload, the assumption 4 ringgit 90 cent, and the total estimated cost for the aircraft is 382 ringgit and 86 cent. But after all purchase has been made, including the glue, the tape and so on, the total cost are around 375 ringgit and 70 cent. This is the cost that we are using for our project. Okay, that's all from us.